takes a whole stack of complex sources and boils them down, really giving you that shortcut to getting informed. And for you, our listener today, this deep dive, well, it touches on something really important, profoundly important, actually, and immediate. You've reached out, sharing some very real, very urgent concerns about safety. Safety in our communities, and let's be honest, particularly in places like schools where our kids should feel secure. Your desire, and it's one we all share, I think, is for truly innovative, practical, protective solutions. Stuff that can just seamlessly blend into everyday life. Feeling as normal as the t-shirt you grab in the morning. This isn't some far-off sci-fi thing we're talking about. It's about using science right now to enhance safety, enhance well-being in ways that are, well, almost invisible. So today, our mission, it's ambitious, definitely forward-thinking, but also deeply relevant. We're asking this big question. Can we actually create protective clothing? And I mean garments as everyday as your favorite t-shirt, maybe a comfy pair of jeans, that offers significant resistance to threats.
And here's the kicker. Can we do this without adding bulky, rigid armor plates? Can we do it by fundamentally changing the fabric itself, its inherent strength, its properties? Imagine your everyday clothes becoming this discrete, integrated layer of defense. It's a huge question, a critical one. And the cutting-edge research we've been digging into, honestly, it points towards some pretty extraordinary, almost astonishing answers.
It really does. And to even start tackling a goal like that, something so significant, so human-centric, we have to dive deep. We're exploring two fascinating, almost, well, magical realms that might seem completely unrelated at first. On one side, you've got the incredible naturally engineered strength, the resilience of spider silk. I mean, that stuff has fascinated scientists for centuries. And on the other hand, we explore the really mind-bending, kind of counterintuitive possibilities of metamaterials. These are entirely human-made structures that, frankly, seem to defy conventional physics sometimes. So this deep dive, it's going to reveal how cutting-edge research is looking to potentially combine these things, not just them, but also other advanced compounds, maybe some established protective tech too, all feeding into what is really a clothing-first approach to protection. It's about leveraging the best of nature's genius, really, and humanity's ingenuity to meet a very urgent need.
Right. And we're going to unpack more than just what these materials are, aren't we? We want to get into the how. How do scientists actually envision synthesizing them, applying them, bringing them together into something coherent, something you could actually wear? We're talking about moving past the science fiction, into real, tangible, okay, maybe early stage, but real material science and engineering. And just to reiterate, the ultimate goal here isn't making traditional bulletproof vests that scream armor. No, it's about fundamentally reimagining the textiles we wear every single day, making them offer this discrete, built-in layer of defense, giving peace of mind without sacrificing comfort or style. So let's peel back those layers. Let's get into the science. Okay, let's unpack this first one then. Spider silk. Wow. For millennia, it's been one of nature's biggest mysteries, right? Just awe-inspiring. It consistently baffles scientists with properties that seem, well, almost impossible. I mean, just picture it. A creature sometimes no bigger than your thumbnail, producing silk that can create these incredible structures, huge scale, amazing resilience.
You mentioned the Darwin's bark spider earlier. Spinning webs, 25 meters across rivers.
That's right, massive spans.
Strong enough to catch insects way bigger than itself. It's just astonishing. So what is it? What makes this natural fiber so extraordinary? What's the secret sauce?
Well, what's truly captivating, scientifically speaking, is its unique combination of properties. It's really unparalleled in the natural world. We talk about spider dragline silk. It's the main structural stuff, the framework for the webs. It isn't just strong. It boasts exceptional toughness. And, for you, the listener, toughness isn't simply about brute strength, how much force it takes to break something. It's critically about how much energy that material can absorb before it actually ruptures.
Oh, okay, like a shock absorber.
Exactly. Think about catching a baseball. A tough glove absorbs the impact, right? It distributes the force instead of just letting it sting your hand or, worse, break something. Spider silk is phenomenal at this, just to give you some perspective. It's about 7 times lighter than steel, but it can be just as strong, if not stronger in some contexts, which makes it, pound for pound, tougher than any other natural fiber we know of, including things like Kevlar, depending on how you measure it.
Wow.
And it's not just one material. A spider's abdomen, it's like this tiny, incredibly sophisticated silk factory. It can produce up to 7 different kinds of protein-based silks.
7?
Yeah, each with distinct mechanical properties. Some are incredibly elastic, designed for stretching, for recoil. Others are highly resilient, meant to handle repeated stress. And some even solidify almost instantly on contact with air. Imagine that. For rapid structural integrity. This versatility is absolutely key to how it functions in nature, and it holds immense potential for the kind of human applications we're discussing.
That's just incredible. 7 types. So how does this tiny little creature manage such an engineering feat? What's the secret that's actually woven into its molecular makeup? What allows it to do all that, the strength, the elasticity, the energy absorption? It's got to be more than just strong threads, right?
Fundamentally, yeah, it comes down to its unique protein fibers. Specifically, scientists call them mass spidroins.
Okay.
Think of these as nature's incredibly cleverly designed protein building blocks. They have this innate ability to self-assemble, basically. They organize themselves into a highly sophisticated hierarchical microstructure. It's a remarkable blend, really, of 2 key components. You have crystalline bishies.
Beta sheets. Like folded protein structures.
Precisely. They're densely packed, highly ordered, incredibly strong. They act sort of like the reinforcing steel bars you'd find in concrete. They provide that immense tensile strength. But then you have the amorphous matrix. This is a more disordered, flexible network. And this is what gives the silk its remarkable toughness and elasticity.
Ah, okay. So 1 part for strength, 1 for stretchiness.
Kind of, yeah. When an impact happens, this whole hierarchical structure allows the silk to excel at absorbing energy. Those amorphous regions, they stretch and deform significantly. They distribute the energy across the entire fiber. It effectively dampens the force instead of letting it concentrate and just break at one point. It's like a finely tuned shock absorber, but operating at a molecular level.
Amazing.
And beyond just structural strength, spider silk shows incredible versatility in nature. Spiders use it for webs, obviously, but also for wrapping prey securely. They even demonstrate this unique pulley effect. They can lift objects many, many times their own body weight using silk.
No way.
Oh, yeah. And what's more, recent discoveries. They're even hinting at potential for advanced sensors. Researchers found that webs can sense incredibly subtle sound vibrations.
So through a web.
Yeah, it suggests these bio-inspired sensing capabilities that could, maybe open up entirely new avenues for integrated smart textiles down the line. It's still early days on that, but fascinating nonetheless.
Okay, the potential just keeps growing. So the idea of harnessing this for human benefit, it's immediate, especially thinking about the safety needs we started with. But the big question always looms. Can we actually make enough of it? I mean, you can't exactly farm spiders on an industrial scale, right? Imagine trying to herd millions of them. So is there a realistic way to scale this up, to get enough for real-world, high-volume applications?
That's absolutely one of the most critical questions for any advanced material: scalability. Can we make enough, affordably enough? And thankfully, recombinant spider silk production is very real. It's a very active and I'd say highly promising field of research. Labs all over the world are engineering various host organisms. Think of them as tiny biological factories. Things like common E. coli bacteria.
E. coli.
Yep. E. coli, plants, even insects like silkworms. They're being engineered to produce these specific spidroin proteins. The basic principle is you insert the spider's silk-producing genes into these hosts, and you essentially hijack their cellular machinery to churn out the proteins we need.
Okay, clever.
Now, admittedly, current lab-scale performance, it still needs to consistently match the precise, nuanced mechanical properties of natural silk, especially in terms of consistency across large batches. That's a challenge.
Right. Nature's had millions of years to perfect it.
Exactly. But the fundamental methods for processing these raw spidroin proteins, they're well established. Techniques like wet spinning and drawing, basically pulling and stretching these recombinant yarns into high-toughness fibers, they're published, they're reproducible. This means that scalable supply is a plausible goal. It's something actively pursued within dedicated R&D pipelines. And the rapid advancement of genomics, our ability to map and manipulate genetic code quickly, that has hugely accelerated this research. It helps scientists crack the complex genetic blueprint of these proteins, allowing for more targeted, more efficient production. It's painstaking, yes, but the progress is significant.
It really does sound like a wonder material, just capable of so much. But when you're working with something that complex, trying to replicate nature, what's maybe the most surprising challenge you've encountered? And where is this recombinant silk being considered right now, especially in areas that align with our listeners' urgent vision for protective clothing?
Yeah.
That whole idea of regular clothes, just stronger, discrete protection.
That's a great question. And honestly, the most surprising challenge is often the sheer complexity of the assembly process itself. We can produce the proteins, sure, but getting them to align and bond in precisely the same hierarchical way a spider does, essentially at room temperature and pressure, that's incredibly difficult. Nature's little bioreactors are just unbelievably efficient.
Right. Hard act to follow.
Definitely. As for applications, well, beyond fascinating biomedical uses, think advanced sutures, maybe tendon repair materials, spider silk is absolutely a prime candidate for ballistics and flexible body armor. It's also being heavily looked at for high-performance athletic wear, where you need extreme durability but also lightweight properties. That's crucial.
Makes sense.
Its inherent high toughness and ductility, the ability to stretch and absorb energy, they're ideal for distributing impact energy over a large area, which is absolutely crucial for preventing a concentrated puncture, whether that's from a sharp object or, a projectile fragment. Imagine for a moment a kind of chainmail-like topology woven from this recombinant silk. A dense, flexible mesh.
Okay.
It wouldn't necessarily stop something by being rigid, but by deforming, stretching, absorbing that energy, preventing a clean penetration. This concept aligns perfectly with the listener's goal. Making regular clothing inherently stronger without being bulky or stiff. It's about building in robust, discrete protection right at the fiber level, making the textile itself the first intelligent line of defense. And this isn't science fiction. It's an active area of materials engineering right now.
Okay, so from spider silk, nature's marvel, let's shift gears. Let's talk about something really on the bleeding edge of human invention. Metamaterials. The name itself, meta, implies beyond, right? So what exactly are these things, and why are scientists getting so incredibly excited about their potential? Especially, again, thinking about our vision for protective textiles. Could these be part of that aha moment for our listener?
That's absolutely right. Meta means beyond. And it's a perfect description because these are artificial engineered materials. They possess properties quite literally not found in nature. Imagine for a second being able to make an object effectively invisible to radar, or creating a lens so powerful it could image individual molecules.
Whoa.
That's the kind of almost sci-fi promise metamaterials hold. They achieve these previously impossible properties by fundamentally changing how they interact with energy waves. See, unlike conventional materials, think steel, plastic, wood, where properties come mostly from their atomic or chemical composition.
Like carbon making steel strong.
Exactly. Metamaterials get their unique characteristics from their structure. Not their chemistry, but their architecture. Think of them as being built from meta-atoms. Now, these aren't real atoms, obviously. They're individual engineered elements, often microscopic or even nanoscopic in size, and they're arranged in a very precise periodic pattern. Crucially, these structural features are designed to be much, much smaller than the wavelength of the energy they're interacting with, whether that's light, radio waves, sound waves, or even mechanical stress waves.
Smaller than the wavelength. Why is that important?
Because it allows the wave to effectively average out the effect of these tiny structures. The wave behaves as if it's passing through a uniform, homogeneous material, but a material with entirely new, often counterintuitive properties that arise from that underlying engineered structure. This structural design freedom is what makes them so revolutionary. It opens up a whole new dimension in material science.
Okay, unusual properties, counterintuitive phenomena. You've got my attention. What kind of extraordinary, almost sci-fi things can these metamaterials actually do? Where does this structural design take us, beyond what normal materials offer?
Right, here's where it gets really interesting. And it fundamentally challenges our basic understanding of material physics. Historically, all naturally occurring materials fall into certain categories based on two key properties. Their electric permittivity, often called epsilon, which describes how a material responds to an electric field,
Okay.
and their magnetic permeability, or mu, which describes how it responds to a magnetic field. Nature gives us materials where both epsilon and mu are positive, or maybe one is negative and the other positive, that's it. But metamaterials, by carefully, meticulously designing their internal structures, they can be engineered to have both negative epsilon and negative mu simultaneously.
Okay, both negative. How is that even possible?
It's purely down to the structure interacting with the wave. This phenomenon, it's known as a negative index of refraction, and it fundamentally changes how electromagnetic energy propagates through the material. It leads to truly counterintuitive effects, like light bending in the opposite direction from what we normally see when it passes from, say, air to water. It defies the basic rules we learn, like Snell's law. You want a mental image. Think of putting a straw in a glass of water. It looks bent, right? That's normal refraction.
Yeah.
Now imagine a hypothetical medium with a negative index of refraction. That same straw would appear to bend in the opposite direction.
Weird.
Totally weird. But this kind of manipulation gives us extreme control over electromagnetic waves, far beyond anything nature provides. Initially, the big excitement around these materials, the stuff that got headlines, was focused on truly groundbreaking applications. We're talking about developing functional invisibility cloaks, at least for specific frequencies like radar, making objects effectively undetectable.
Seriously, like Harry Potter.
Well, for radar waves, maybe not visible light easily, but also things like super-resolution lenses that could see details far smaller than the wavelength of light itself, potentially imaging individual molecules. Think about the implications for medical imaging or microscopic analysis, revealing structures we've never seen before.
Okay, negative refraction, invisibility cloaks for radar, super lenses. That's incredible stuff for optics, maybe stealth, maybe medicine. But for our listener, the core question remains, can these principles, this whole idea of function through structure, actually extend to the kind of physical protection we need for clothing? How do we get from bending light waves to, say, blunting a physical impact, like a punch or a knife or a projectile? That seems like a completely different ballgame.
It does seem different, but that's a crucial point, and the answer is yes, absolutely. The principles extend remarkably well. While, the initial buzz and maybe the public imagination really latched onto those invisibility cloaks and super lenses, the core principle, function through structure, is incredibly versatile. It applies to many types of waves, not just electromagnetic ones. This includes mechanical waves like the shock waves generated by an impact, and also acoustic waves, sound. And this versatility has directly led to the development of mechanical metamaterials.
Mechanical metamaterial. Okay, so not about light.
Exactly. These aren't designed to manipulate light or radio waves. They are architected microstructures, meaning their internal geometry is precisely designed and controlled, often at a tiny scale. They often take forms like microlattices or auxetic textiles.
Microlattices, like tiny scaffolding.
Sort of, yeah. Imagine a tiny 3D network of interconnected beams, like a microscopic truss bridge, but with a highly optimized geometry designed for specific mechanical responses, and auxetic materials. These are really counterintuitive. When you stretch them, they actually get thicker perpendicular to the stretch.
Thicker when stretched. Most things get thinner, right?
Precisely, like stretching a rubber band. And when you compress an auxetic material, it gets thinner, contracting inwards. The classic example of a wine cork. You push it into a bottle, it bulges outwards, making it hard to push in. That's a positive Poisson's ratio.
Right.
An auxetic material has a negative Poisson's ratio. If you squeezed it, it would actually contract inwards, potentially making it easier to insert or behaving differently under impact. So these mechanical metamaterials, they can be 3D printed or architected at micro and nanoscales to dramatically improve specific energy absorption. They let us finely tune that Poisson ratio, control how the material deforms, and even dictate how it fails under stress, maybe crushing progressively rather than shattering. This means they can be designed to absorb and dissipate impact energy in highly controlled, incredibly mass-efficient ways. They can far outperform bulk solids of the same weight. Imagine a structure that crushes in a specific optimized sequence to soak up the maximum energy. Now, if we connect this back to the bigger picture, to our listeners' vision for safer clothing, these mechanical metamaterials offer huge potential. They could form an incredibly efficient intermediate structural layer within a textile, or maybe even be integrated as printed microarchitecture on or into the textiles themselves.
Wow, printed right onto the fabric.
Potentially, yes. Essentially multiplying the energy absorption and blunting penetration without adding significant bulk or rigidity. They give us the ability to precisely tune how impact energy is directed, how it's spread out, how it's absorbed across a garment. This makes them incredibly relevant for creating discrete, effective, wearable protection. This ability to manipulate mechanical waves at the structural level, it's truly revolutionary for protective materials.
Okay, so we've got the amazing toughness and energy absorption from recombinant spider silk. We've got the incredibly clever engineered impact manipulation from mechanical metamaterials, but building this next-gen protective textile. It feels like it needs more, right?
Yeah.
What else is in the toolkit? But other compounds, fluids, maybe even established materials are scientists looking at to play a critical role in this hybrid vision, especially for that discrete, everyday protection.
Absolutely. It's rarely just one magic bullet. A critical component, one that's been widely researched and is highly reproducible across many labs, is shear thickening fluid, or STF.
Shear thickening fluid. Okay, what does that mean?
Right, so these are typically what we call non-Newtonian fluids. Their viscosity, their thickness, or resistance to flow changes under stress. Usually, they're made of very fine particles, often silica-based, like tiny glass spheres suspended in a carrier liquid. A common one is polyethylene glycol, or PEG. Now, under normal, low-stress conditions, like when you're just walking around wearing the garment, the STF flows freely. It behaves like a normal liquid. The particles just slide past each other.
Okay, so it's flexible.
Exactly. But upon sudden high-rate impact, think a projectile hitting or stab from a knife, even a very hard fall, those suspended particles instantly jam together. They lock up. This causes the fluid to rapidly, almost instantaneously, become much, much more viscous. It behaves almost like a solid for a very brief moment. Milliseconds.
Ooh, it just locks up solid.
Effectively, yes, for that instant of high shear. This rapid and importantly reversible change in viscosity is the key to its protective power. Numerous studies from places like the University of Delaware and other leading groups have consistently shown this works. If you impregnate traditional woven fabrics like Kevlar or that ultra-high molecular weight polyethylene, UHMWPE, we'll talk more about with STFs, you reliably increase both ballistic and stab resistance. They significantly improve the V50. Remember, for our listeners, that's the velocity where there's a 50% chance of penetration. Higher V50 means better protection.
Right, higher is better.
And crucially, STFs also dramatically reduce something called yarn pullout. This is a common failure mode in normal textile armor.
Or pull out.
Yeah, imagine the impact hitting the weave. Sometimes, instead of breaking the fibers, it just pushes them aside, pulls them out of the weave structure, creating a hole for the projectile to slip through.
Ah, I see, like making a gap.
Exactly. By stiffening instantly, the STF essentially glues the fibers in place during that critical moment, forcing them to work together and distribute the load much more effectively. This makes STF impregnation a proven, reproducible, and actually quite scalable finishing step. It can drastically enhance a fabric's ability to resist piercing or high-energy impacts without making it inherently rigid or uncomfortable for everyday wear. It kicks in only when needed.
That sounds incredibly clever, like an instant invisible shield that activates on demand. But you mentioned it's reversible. If these fluids become solid-like on impact, does that affect the fabric long-term? Like, does it stay stiff in that spot? Or does it fully recover? And what about just wearing it? Does adding a fluid layer make the fabric feel, heavy or clammy or less breathable? That seems important for regular clothes.
Those are excellent, very practical questions. And yes, they are absolutely front of mind for researchers developing these. The beauty of most STFs used in these applications is that they are generally reversible. Once that high impact force is gone, the particles de jambes, they unlock, and the fluid returns to its normal low viscosity liquid state.
Okay, so it bounces back.
It does. The fabric doesn't become permanently stiff in the impacted area, so it maintains its overall flexibility, which is crucial for comfort. Now, as for comfort and breathability during wear, that's definitely where the engineering challenge lies. Researchers are constantly refining the formulations, the type of carrier liquid, the size and concentration of the particles. PEG, for example, is often chosen partly because it's relatively inert and allows for some degree of moisture vapor transmission, which helps with breathability. The goal is to apply the STF in a way that creates a functional protective layer, but one that's thin, lightweight, and doesn't feel uncomfortable or, as you said, clammy. While it might add a small amount of weight compared to the untreated fabric, the aim is definitely to avoid that unpleasant feeling. Significant progress has been made in creating STF-treated textiles that feel surprisingly normal. It's a key area of ongoing refinement, for sure.
Okay, good to know. So, beyond that sudden stiffening of STFs, what about materials that can just soak up energy, like a high-tech sponge, maybe?
Yeah.
Something that absorbs and dissipates the force before it even gets to the deeper, more critical layers, or the body itself.
Exactly. And that's where another class of materials comes in. Tough nanofibrous hydrogels. And related things like bicontinuous tough gels.
Hydrogels, like in contact lenses, but tough.
Sort of, yeah. But engineered for extreme resilience. Pioneering groups, notably out of MIT, have developed these. Think of them as incredibly resilient, flexible networks. They're polymer-based, but they hold a lot of water within their structure. Imagine an advanced, super-absorbent sponge, but at a microscopic level, and engineered to be exceptionally strong and elastic under high strain rates.
High strain rates, meaning fast impacts.
Exactly. They excel at absorbing and dissipating energy from sudden, violent impacts. They deform significantly, stretching and compressing, effectively soaking up that energy. They're ideal as a kind of sacrificial layer, a layer designed to deform and literally bleed off a huge amount of the impact energy before it can reach deeper structural layers in the garment, or more importantly, the wearer.